If asked in interview, can you explain the backtick timescale syntax in Verilog? If asked in interview, do you know how many data types are there in Verilog? If asked further, do you know how many format specifiers are there to print various kind of data types including time in Verilog? Stay tuned till the end of the video to know all the answers.
Hey guys, welcome back. In today's episode, we are going to discuss the below points. Basic data dealing in Verilog. So here we'll talk about how many types of data are there and how you can deal with them. Next, we will go in detail of data and literals. Next, we'll talk about the different data types handling. Next, we will go explicit detail of time, registers and variable usage. Next, we will provide example for literals and their interpretation. Next, we will talk about how we can use the format specifiers to print the different data formats and variables during a simulation. Next, we will talk about very important directive, that is the backtick timescale in simulation with examples, and it has to do with the time data type, whatever data type we are talking about here, and we will also talk about that. Next, we will go through a code example of the backtick timescale with different variation and we will compare the outputs. This part will be very important for you in case of both simulation as well as for the interview preparation. And this part will be important for your understanding as well as interview purpose. So the entire episode is very important. Pay attention properly, and we're done here with the menu. So let's move on to the next slide. Basic data dealing in Verilog. Here you can see the table. What are the basic data that we deal in Verilog? That is 0, which is a logic 0 or false condition. Logic 0 when we are exchanging data among the logic gates connected by nets. And it is a false condition when we are using it in the if condition. Next is 1, it's a logic 1 for circuit connection and it's a true condition for the if condition. Z is the high impedance state, and this is strictly for the circuit connection and circuit data exchange among the gates. It is used for tri-state buffer, and X is the do not care or unknown value. These are the 4 basic data that we deal in Verilog. We can have different representation of them in terms of octal or hex or decimal. However, when we are dealing in the circuit level, we will deal with these 4 basic data values, or since it's a logic circuit, you can say we will deal with all these logic values. So we are done here with this particular slide. Let's move on to the next slide. Data and literals. In Verilog, we have different way of representation, use and display methods for various number system inside a single Verilog program. The value Z and capital Z stand for high impedance and X and capital X stand for uninitialized variables or nets with conflicting drivers. So this is a perspective for the digital circuits for Z and X. Now, what are the literals? We have binary literals, and how we write? First, we write 2, that means what is the width of the data, right? Then we have a tick here, and then we have B. B means binary, and then we have 1 and 0. So 1 goes here and 0 goes here. This is the binary literal. 2 is the width here. B is the type of the data, and the content of the data is 1, 0. You can see the graphical representation here on the right hand side. Now let us see what are the other literals are there and how we write them. Octal literal. Here you can see 2 is the width, O stands for octal, and the content is 17 in octal. Next we have decimal. So decimal do not need such kind of format specifier like B or O, what type of data. You can write directly the decimal number, or in case you want to write, you can write D. D represents decimal and the content is 9, or you can write in this way. We'll talk about this separator in upcoming slides, so you'll come to know. Next is the hexadecimal literal. So here the width is 3, type hexadecimal is defined by H, and the content of the variable is 189. 189 is not in decimal, it's in hexadecimal. So be careful and pay attention. This 17 is in octal, this 189 is hexadecimal, and here it is in decimal. All these type of data we can represent through the literals. Literal is a term for Verilog, where we use it to represent the different number systems here, and we write them with the help of the syntax that is available inside the Verilog. We are done here with this particular slide, so let's move on to the next slide. Data types handling. Here, let me give some examples. First one is the real, then ABC. So ABC to be real. Real is a data type. You know, in case you are familiar with the C language, you might know that there are real numbers, integers, etc. We can also define the integer with the keyword integer, and then JK are the integer variable. So here, if we type real keyword here, it will mean that all these variables are real. That means some decimal format 3 or 2.3 is a real number, right? Our integer is 2 here. So JK can be this type and ABC can be of this type. So integer can be of this, the array of integer variables, right? I 1 up to 32. So this is the bus representation in Verilog. However, this can be used for integers to represent the array. Range is a type range, that means a register. We have already talked about this kind of registers and compared with them the nets, that is where in last episode. So here the range is there and array 3 down to 0 is there and it's a range. Again, we can have integer I initialized here in the declaration itself. I equal to 0 I have written here. And we have real R2 equal to 4.5, R3 equal to 8. They are initialized at the declaration. Then the unique data type that is exclusive to Verilog as compared to its programming language counterpart like C, Perl, etc. is the time variable. So here we have the data type time and we have a time variable. Start time is 40. 40 is the value of the prefix and it has to be multiplied with the time unit, and the time unit has to be defined by backtick time scale. Next we have integer a equal to 1. It's a sign number 1. Size is 32-bit. Next we have integer a equal to -1. We have the initialized. It is sign number, that is -1. Size is 32-bit in 2's complement format. These are a couple of examples of data types that you can write in Verilog. So here we have talked about integer, real, time, all these type of data type handling in Verilog. So we are done with this particular slide. Let's move on to the next slide. Here, time, registers and variable usage. Time, we have time declaration and we have a time variable new time, and time and integer are similar in functionality. Time is an unsigned 64-bit used for time variables, and here we end our comment. So this was a comment. If you remember the comment, multi-line comment starts with a slash, then asterisk, and then a asterisk and a slash. It ends. Next, we have range representation 8 star 15 down to 1, and it's a string. How we can deal with a string in Verilog? This way we can do it. This is a question for your interview. This defines a vector with a range. So the range is MSB of the expression down to the LSB of the this way. Let us look into some examples here. We have an initial block and begin keyword here. And then we have a equal to 0.5. It is same as 5.0 e minus 1, the real variable. Then b, we have 1.2 e12. So 1.2 into 10 to the power 12. Then we have c as 26.19 underscore 60 underscore e to the power minus 11. Dash r used for readability. We have reached to the next line. String is, we have a string example under the double quotes. This is a string. Remember, we have defined the string here. Then we have the new time, right, equal to $time. So whatever $time contains, it goes to the new time because we have defined the new time variable here. We end here the initial block. This is a kind of example how to deal with the different data types which are new to you, like the time one in Verilog, apart from whatever concept that you borrowed from your programming language. So here we are done with the example. Let's move on to the next slide. Literals and interpretation. Examples. Here goes our table. So here we have range 1 down to 0, A, and we have 2 tick B. These are two binary numbers. The first one is this and the second one is this. So the value is actually is this. Underscore is ignored because it is used for the readability. We have range 3 down to 0, A, that is 4 tick D1, and this is 1. D is for decimal, right? And we have range 5 down to 0, A. It has 6 is the width and octal, and that is 12 is the octal content. So here it is the octal value and O is used for octal. We have range 5 down to 0B and we have 6 tick H1F and the content is this one in hexadecimal, or rather we expressed it in binary. Here we have expressed it in hexadecimal. Here you can see all the data are represented in binary. The H is for hexadecimal, and then we have 4 down to 0A, which is a range type variable, and the content is represented by the literal 5 tick BX. This has a width of 5 and the content is X, so it is 5X. X is the don't care condition. Range 4 down to 0A, 5 tick BZ. So here similarly the width is 5 and the content is filled up with all Z. Z is high impedance. And here we have 4 down to 0A, which is a range type, and we have the content value is 5 tick BX01. What does it fill? 5 is the width, so the entire width is 5. X occupies apart from whatever 01. So 01 is written from the right hand side, and in the left hand side the rest of the places are filled up by X. The width is defined by 5, so it is XXX then 01. That is high impedance. So here we have given the literal examples and how we interpret them. I hope this is a good page for you or a good slide for you for your understanding how we can write in different literals in Verilog. We're done here with the examples. Let's move on to the next slide. Printing and format specifiers. Here goes our table. So folks, you have came across the $monitor, $display, etc. I have used in the first couple of episodes where simulation has been directly run through the Vivado or the Icarus Verilog. Here you have come across couple of format specifier for printing. I have used in the test bench, and here I have the exhaustive list. So to print the hexadecimal numbers, right, you have to use the format specifier %h or %H. For decimal format, you have to use the %D or %D. For binary format, you have to use the %B or %B. For hierarchical name means generally a net has a hierarchical name. Okay, so for that you have to use %M or %M. To display something as string, you have to use the %S or %S. You want to display the time value, you have to use the format specifier %T or %T. Display the real in a decimal format, you have to use the %F or %F. Now to display the real in an exponential format, that is 1E, this kind of format, you have to use %E or %E. And decimal means is 1.2, and here this is 1E10. So this kind of values you can print with %E. So folks, this slide contains the exhaustive list of all the format specifier that you can use for your print statement inside the test bench, and these are good for your debug. We're done here with this particular slide. Let's move on to the next slide. Backtick timescale in simulation. This is a very important slide. Please pay attention. The backtick timescale has two components. First one is time unit, then comes a slash, and then the time precision. The unit is whatever unit has it, right? And the precision is the fractional value up to which it can count under this unit. Time unit is the unit of present time unit, the unit of present simulation time or delay insertion. So that it is the unit, one single unit. And time precision, the fraction of the time which is measured with accuracy. That means how far we can go in the smaller direction to measure some time. Backtick timescale is used for base unit of measurement and precision of time. Print timescale system task is used for display time and precision. In case you want to see this format, right, you have to use the print timescale. Time and real time system functions return the current time and the default reporting format that can be changed with another system task, that is time format. You have came across all these different tasks which are predefined in the Verilog library. In case you want to go to the details, please check the LRM, that is the language reference manual. And for Verilog, since now Verilog is the subset of the system Verilog, you have to look for the system Verilog LRM. Here we are done with this particular slide. Let's move on to the next slide. Backtick timescale case example. We will talk about different case examples of the backtick timescale. So here again, the timescale, the backtick timescale directive has two parts. One is the time unit, another one is the time precision. That means how far you can go downwards in the precision wise. Let us see some examples. First one, backtick time scale 1 nanosecond and 1 picosecond. So this is the unit is the 1 nanosecond. So this is the unit for your time simulation. And this is the precision or the fraction up to which it is measured. So you can see nanosecond to picosecond. It's 10 to the power minus 3 difference, right? Next, we have time scale, backtick time scale with 10 microsecond by 100 nanosecond. That means this is a time unit that should be there for the unit step for your simulation. And this is a fraction up to which accurately time should be measured. And here the backtick time scale again comes with 10 nanosecond by 1 nanosecond. So 10 nanosecond is the unit in which your simulation progresses as per the unit time. And when some difficult calculation or accurate calculation is needed, it goes down up to 1 nanosecond accuracy. That means your simulator will calculate up to 1 nanosecond. So these are couple of examples of the backtick time scale that is used in Verilog simulation. This is very important. This is asked in interviews, so get prepared, and also you can think of any tricky thing or tricky question that can come up to your mind and be prepared for your interview. Here we are done with the particular slide. Let's move on to the next slide. Backtick time scale code example. Here we'll go through a code and later we will see its output itself in this particular slide, not in the simulator. And there we can see how the backtick time scale impacts the calculation accuracy. So first we have the 1 nanosecond by 1 nanosecond time scale unit and the precision. Alternatively, in the second set of simulation, we are going to use 1 nanosecond by 1 picosecond. Then we have our module test bench is abbreviated as TB, and we write reg val. We write our initial block, and here we print our time scale. Initialize the signal to be 0 at time 0 unit. Val less than equal to 0 is the kind of assignment, dynamic assignment that you do, right? It's not a continuous assignment. Then we advance by 1 time unit. Displays a message and toggle the value. Here we have #1, that means we are proceeding with a 1 time unit delay, and we use the display that is equal to %t at time #1 with real time. You can see real time we are using here. Whatever time we are using, that can be print through the real time. Next, we assign 1 and advance by 0.49 time unit and toggle the value. So again, in the similar way, we are putting it here, and we are putting a display command %t here, and we put real time here. And next we change the value to 0. That means you can see 0 to 1 here, and then 1 to 0 here. So we proceed with the time unit, which is defined by this, and then we toggle the value. So this way our code proceeds. So the code is not finished yet. Let me show you the remaining part. We advance by 0.50 time unit and toggle the value. Here it is #0.50 and display t%0t at time, this one with the real time. And then we again toggle the value. The earlier value was 0. From there we have toggled it to 1. Again with advance by 0.51 time unit and toggle the value. So here is the #time delay, and here is our display command. So here we toggle from 1 to 0. Let simulation run for another 5 time unit and then exit. So here we have #5, display this, and then we end our block, and here end our test bench module. So what happens when we simulate this code with two different backtick time scale options, that is which we have shown already. Let us see in the next slide. Simulation output comparison. So what happens for backtick time scale with 1 nanosecond by 1 nanosecond? So here is the out. You can see at time #1 is 1, time t equal to 1 at time 4.49. Time 0.5 is also this, right? So this is kind of proceeding, right? So here you can see it is not changing here in these two values, and here it is also some kind of difficult to interpret how much accurately we have changed. Let me explain here. Since the precision is 1 nanosecond, the time scale can proceed with multiple of 1 nanosecond unit only. Hence, the fraction of nanosecond cannot be measured. You can see here we have proceeded through fractional, but here we can see no fraction here. Now let us see what happens with the time scale 1 nanosecond by 1 picosecond. That means we have increased our precision up to 10 to the power minus 3 here. Here comes our output. Here you can see everything in the code remains same, and here you can see this with the time scale we have printed that whatever time scale, the print time scale command, we have printed 1 nanosecond by 1 nanosecond, and here you can see with the print time scale we have 1 nanosecond by 1 picosecond. So here you can see equal to 1000 at 1, 1490 at this, 1990 at this, and 2500 at this. These keep on adding, right? Because we are adding delay, so these are getting added to the initial time, right? And that's why whatever is changed, you can see the reflections here. That equal to 7500, we end our simulation. So here, let me summarize it. Since the precision is 1 picosecond, the time scale can proceed with multiple of 1 picosecond unit, and what the difference here versus here you can see, because only change in the test bench is this versus this. So you can see how accurately you are able to print or measure the time. Here there is no accuracy, 1 to 1, 2 to 3, so you do not know exactly how much precision it has moved forward. But here you can see 1000, 1490, 1990, 2500 and 7500. Hence, fraction of nanoseconds can be measured. So this is very crucial for you. Why? Because in Verilog simulation, when you see a waveform through the VCD file or maybe your inbuilt simulator like Vivado, if you do not choose the time scale properly, you will not be able to debug in case of different changes. Say you want to measure something like hold value or setup value or difference between the two changes in two different input changes or output changes. That becomes very difficult for you. So the time scale, this time scale and its precision, the unit and its precision is very, very important. Generally, this is very good to know for your simulation and debug, and this question is asked in the interview, that whether you know the importance, significance, the usage and how they become different when you have the different unit and precision. So this is a very small example. You can write down or memorize the example and give the output so that your interviewer is satisfied with this thing. Obviously, I will ask you to try out the code, write down the test bench in either Vivado or Icarus Verilog and simulate it. So I think in the first or second episode, we have shown how to simulate using the Vivado or Icarus Verilog. I think up to this episode, you are well able to write a code and simulate. So hence I am not showing anything here. I'll suggest you to try it out at your end, write the code and see these out and do your changes and see what happens, and try to explain whatever changes you have made and accordingly whatever the difference you see in between this and this. So that will help you out to prepare for your interview. Here we are done with the particular slide. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.